All right, so section 5.2, Introduction to Trees. Our vocabulary for this section is a cycle, a tree, a root, and a rooted tree. So taking a look at an introduction to trees, our basic definition is a tree is a connected graph, but there aren't any cycles in the graph. And so kind of think about the idea that you can't start at one spot. So a cycle is a simple circuit in which one vertex, the initial, is repeated and is repeated exactly once. So because on a tree, you have no way to get back to where you started. So let's just say, let's continue the conversation a little bit, and this will make more sense. So on example 1, identify all simple paths from vertex U to vertex V. So if we start at U, there's only one way to move our way across and get to V. There's no way to make it back, and it's only going to hit U once, and it'll make it to your terminal, which is V. And so that's an example of a tree. There's no cycles, but it's a connected graph. All right. So for figure A, identify a simple graph. So we got that right there. And then the simple graph here would just be here, 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 and here. All right. And then they want us to make a connection. That's just something we're going to use in our explanations or our theorems for this section is that we want to look at the number of vertices versus the number of edges. So vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. This leads us to theorem 14, which we'll see in just one second. On this guy over here, we see vertices and edges. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Count our edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So hopefully you're seeing that there's going to be a possible pattern there that we can look at. Sorry about that. Let's clear that. Go to the next slide. All right, so we have 3 theorems that come about from this basic, that we're going to apply, that come about from this basic exploration, and that is a tree is a unique simple path between each pair of vertices. All right, so that's confusing because it says each pair of vertices, but just going from your first location to the second location, the initial to the terminal. We have a fact that in a tree with n vertices, there's precisely n minus 1 edges. So I'm sorry, I said theorem 14. It's theorem 6 and theorem 7 that say that. So we saw that a minute ago because we looked at our relationships between our vertices and edges. On each one of these, we had, and I erased this, I apologize, but on this guy, sorry about that. On this guy, I believe that our edges was equal to 11 and our vertices is equal to 10 or vice versa, something like that. And we had this relationship where it was always 1 less. So when we cruise on to the next piece, sorry about that, then we see these guys come in true. So T is a tree, T is connected, has a unique path between, I'm sorry, I'm on the wrong one. So T has n vertices and n minus 1 edges. And so we cruise here and we see that theorem 7 says the following statement about graph T with n vertices are equivalent. So T tree, T is a tree, T is connected with a unique path between a pair of vertices, and then T is connected with n minus 1 edges. And that's that n minus 1, the number of vertices versus the number of edges. All right, next, that takes us to rooted trees. Sorry about that. I'm gonna hit pause for just 1 second. I'll be right back. I'm actually gonna stop that video right there and make a second one for rooted trees. Thanks.